Can you please share the screen? So welcome all today for today's tutorial for the week 9 for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR Bombay. So the topics that I intend to cover would be mostly related to unconstrained optimization, Okay. Then Prasun, now I can't. Earlier there was some noise coming from your side. You have anything to say? You can type it in the chat box. I think there was some issue with your mic. Okay, then we'll move to KKT conditions. We'll talk about steepest descent method. And here I'll talk about, I have talked earlier, but I'll again talk about a perspective that is useful for machine learning applications. Okay. Then we'll look at a variant of this, which is known as Newton method, and also talk about why the Newton method is not very common in machine learning community, although it's good, but why it is not very common. And yeah, we'll talk very little about penalty functions, and we'll try to solve problems related to assignments based on these topics. Okay, so if it has been posted on discussion forum, I think the official TA will answer to it. If not, towards the end of this lecture, I'll have a look at what is that question, and we'll try to answer your question. Okay. Or let me have a look at it. What is the question? If it's a small one, then we can solve it right now, or we can try solving it towards the end of the lecture. So this is week 8, question number 10. Let me have a look. Okay. So what is the doubt that you have related to this question? It says in term. I didn't got you, Ashwin. Can you please be more specific? So which of the following commands perform a series expansion up to 5 terms? So when you have series expansion, you expand sin x to some terms and then you have some small error, right? So the question is you have to expand up to 5 terms. That's fine, right? So 5 terms would mean that's okay. So you're saying that it should be 4 order, right? This is what you're saying? Yeah, I partially agree with you. So if it is related to which option is correct, that can be only done by official TA. So you have posted a question. I'll write an email to the official TA so that he or she replies to your this query. I'll definitely write. It would be resolved. Don't worry about it. Okay, so let's begin with our today's discussion. Yeah, so first of all, when we talk about optimization, we talked about this last week also. Whenever we talk about optimization, we talk about something of this format. So we have some minimization or maximization, some f of x, and subject to some constraints. These constraints are represented by gi of x less than equal to 0. Okay. So every time it is not necessary that your problem have some constraint. Okay. For example, when you look at the loss function of some of the machine learning algorithms that you might be familiar with till now. For example, let's say linear regression or logistic regression. Okay, regression. There you had some loss term. Let's represent it by a better variable. Let's say this is j is equal to summation over all the data points loss of f of xi comma yi, right? So here you just wanted to minimize your j, but you didn't had any additional constraints with you. Okay, so these kind of problems where you don't have any constraints, that is called as unconstrained optimization. So your unconstrained optimization would look something like minimize some or maximize some f of x. Okay, so this is what we mean by unconstrained optimization. Okay, so I'll try to relate this concept with whatever you have learned in class 12. Okay, so what is feasible or infeasible solution? This is not very relevant for your unconstrained optimization, but a feasible point. So if you have, let's say, let's call this P1, this is program 1. So for P1, you have some gi of x greater than, sorry, less than equal to 0. These are known as constraints, right? So if you have a point x bar which satisfies gi of x is less than equal to 0 for all I, so that means that your point x bar is satisfying all your constraints, right? So these kind of points are known as feasible points. So feasible points are nothing but points which satisfies all your constraints. Okay. And what is your feasible set? Feasible set is your collection of all feasible points, right? Similarly, you can define infeasible points or infeasible set of points which sort of violates at least one of your constraints. Okay, so now I'm just right now revising the definitions. We'll move to the questions very soon. So what is known as a stationary point? So let's say when you were in your class 12, when you were, let's say, asked to minimize or maximize, let's say, f of x is equal to x cube minus 3x. Okay. So what you used to do is, you used to find f dash x equal to 0. Okay. So what you would have done, you would have done 3x square minus 3 is equal to 0, something of this sort, right? So we have a very similar definition when you move from one variable to multivariable, but now because one variable derivative is replaced by gradient, so we define stationary point for multivariable function as gradient of f is equal to 0, right? So intuitively, if you look at it sort of graphically, okay, so what is happening is, so at some, so when do you have sort of a stationary point? A stationary point occurs, generally there is one more situation, when your function, if you look at this point, to the left of this point your function is decreasing, right? That means its derivative is less than 0 because it is decreasing, right? And if you look at this portion, your derivative is sort of increasing. Okay, so there is a very beautiful property that is associated with derivative, that if, let's say, if your derivative is less than 0 at some point and your derivative is greater than 0 at some point, then there must exist a point where your derivative is sort of 0. Your derivatives can't jump value. Okay, so this is a very beautiful property that is associated with the derivative. So you know, whenever your function is continuous, your functions can't jump values. But even if your f dash is not differentiable, your f dash satisfies this property that there would be a point where your f dash is equal to 0. Okay, so that is the point where you have sort of your minimum point or maximum point, because after this point your function has started increasing. Okay, because the derivative has become positive. and before this point your function is still decreasing, right? So this is the point where towards the left it is decreasing, and after that it has started increasing. So this is the point of minima. Okay, so this is the idea. And if you translate it to a multivariate function, then what is happening along every coordinate, the same thing is happening. That, like, if you look at along x-axis, same thing is happening with the function. If you look along y-axis, same thing is happening with the function. Okay, so this is sort of a necessary condition, not a sufficient condition. So what is meant by necessary condition? Necessary condition means that if your x, let's say, is a minimum point or a maximum point, then it must satisfy this property, that your gradient of f at x is equal to 0. But there can be other points also which satisfies this property but is not a minimum or a maximum point. Okay, so we can look at it via an example. Okay, so let's see that. Let's look at f of x is equal to x cube. Okay, so if you look at this function, so the graph would look something like this, right? So it comes here and then again it goes. So at 0, f dash x is 0, right? But this is actually not a minimum or a maximum point, but it's still a stationary point, right? So just to summarize, a point is called as a stationary point if gradient at that point is equal to 0. And this is a necessary condition for a point being local minima or a local maxima. Okay. Now you have a similar necessary condition. If you don't want, somebody don't want to use first order principle, then you have a second order characterization which says that if your Hessian matrix is positive semi-definite, then also you can say this is also a necessary condition. So, like, if you have all the necessary conditions, then this might not serve your purpose. You are actually looking for a sufficient condition. So let's say you want to solve some minimize f of x, then you want some certain condition or a certain algorithm that if you will follow this, then you will land up on a minimum point. Okay, so the sufficient condition for finding a local minima is that your x bar is a local minima or similarly a local maxima if, first of all, x dash is a stationary point. What does this mean? That your gradient of f is 0 at that point and your Hessian is positive semi-definite. Okay, this is Hessian. And if you talk about maxima, your gradient should be positive, negative, sorry, it should be negative semi-definite. Now, if you relate it to what you studied in class 11 or 12, so how you used to say that your point is a minimum or local minimum or not? So first you need to find f dash x is equal to 0. Then you used to do second order test, that if your f double dash x is greater than 0, then this is a minimum point, and if f double dash x is less than 0, then this is your maximum point. And similar thing is happening over here. Just f dash x is replaced by Hessian, and your greater than equal to 0 symbol here is replaced by positive semi-definiteness. Okay. Any doubt till this point? Okay. So just a very quick summary. If somebody gives you an unconstrained optimization problem, that is, let's say he gives you minimize f of x, then what you are going to do, first of all, you are going to find out its gradient, equate it equal to 0. Okay, and find all the points that satisfies this. Let's say there are 2 or 3 points that you found out that satisfies this property. Okay. In the next step, what you will do, you will calculate Hessian. Okay, and you will check positive semi-definiteness of your Hessian at all these 3 points, x1, x2, and x3, and based on that, you will infer whether this point is a local minima, a local maxima, or none. There is a possibility that your Hessian turns out to be none of these. Okay. Okay. So yeah. One more thing that I want to include here. Last time I think I messed up something that I want to correct, right? So last time, this is a sort of detour which I mentioned incorrectly last time. So last time what I mentioned is, let's say A is a symmetric matrix. Let's say this is 1, 2, 3, 3, 2, 4, 5, 5. Okay. Now, if you want to check whether this matrix is positive semi-definite or not, what I told you is that you will check all the principal minors, and if all your principal minors are greater than equal to 0, then you can say that your matrix is positive semi-definite. Okay, till this point we were correct. Whatever I said was correct. But when I told you about how to check negative semi-definite, I told you that principal minors should be less than equal to 0, which is incorrect. Okay. So what is the correct way to check whether your matrix is negative semi-definite or not? So your first order minors, so your first order principal minors. So how would you obtain first order principal minors? That you would obtain by deleting 2 rows and 2 columns at a time. So all these should be greater than equal to 0. Your second order minors, principal minor, should be less than equal to 0. Again, your third order principal minor should be greater than equal to 0. So you can see there is a pattern that your minors should be of alternate signs when you talk about negative semi-definiteness. Okay. There is an easier way to check negative semi-definiteness, because this can be confusing. So which one do you have to check for the alternate signs? A simpler way is, if you want to show that your A is negative semi-definite, you just show that your minus of A is positive semi-definite. So you just multiply your matrix with my negative sign, okay, and then you check whether all its principal minor, all the principal minor of minus A is greater than equal to 0 or not. Okay, so this is an easier way to go about this. Am I clear about what mistake I made and what is the correct way to check negative semi-definite? Yes. Anybody has any doubt can. Uh, okay. Okay. So we are sort of we know now how to solve unconstrained optimization. Now let's look at two broad way to bifurcate any optimization problem. Okay. First way is using linearity. Okay. So let's say you have some optimization problem. Let's call it P1. That is, minimize some f of x subject to your constraints that gi of x is less than equal to 0. Okay. Now you can bifurcate this into two classes. First is linear programming problem, and second is non-linear programming problem. Okay. So what is meant by linear programming problem is that all your f and gi, so whatever your f is and all your constraints, if they are linear in nature, then that sort of optimization is known as linear programming problem. Okay. If any of these, let's say if any of the constraints or your objective function is non-linear, then you will call your setup as non-linear programming problem. Okay. So this is one bifurcation. Again, for nonlinear programming problem, you have a special sort of type which is known as quadratic programming problem. So if your f of x is quadratic in nature and all your constraints are linear, okay, so this would look something like minimize C transpose x plus x transpose qx subject to gi's of x is less than equal to 0, where gi's are linear. Okay, so this kind of programming problem or optimization problem is known as quadratic optimization or quadratic programming problem. Okay, and we know some useful tricks to tackle these kind of problems. That's why we have classified this as a special class of programming problem. Okay, so so this was based on this bifurcation that we talked about was based on linearity. We have another bifurcation which is known as convex optimization problem, and another one is non-convex optimization problem. Okay, so let's say you have the same programming problem that we had over here, that is minimize f of x subject to gi's of x is less than equal to 0. Then it is called as a convex optimization problem if all f and gi's are convex. So your f as well as gi's are convex, then it is known as convex optimization problem. Remember, when we talk about this definition of convex, then we talked about optimization problem in a specific form. That form is minimize f of x, gi of x is less than equal to 0. If you are able to write your programming problem in this form and your f and gi's are convex, then you can say that your programming setup is your convex optimization. Okay. So if your, let's say this problem was sort of, let's say this was maximize f of x subject to gi of x is less than equal to 0, and you want to check whether the problem that is given to you is a convex optimization problem or not, then what you need to do is first you need to transform this into the standard form. Okay, so you know that maximizing f of x is same as minimizing minus f of x. Okay, so what you will do is this is equivalent to minimizing minus f of x subject to gi of x is less than equal to 0. Okay, so now you want this thing to be convex optimization problem. So what does that imply? That your minus f of x should be convex and all your gi should be convex. What does that mean? That minus f is convex and gi's are convex. So minus f being convex means f is concave, right? So if you want to say optimization problem of this form, if you want to label it as a convex optimization problem, then your f must be concave and all your gi's must be convex. Okay. So here are some more possibilities. Let's say you have something like maximize f of x subject to gi of x greater than equal to 0 this time. Then what you can do is you can just do this. You can rewrite this as minimize minus f of x subject to minus gi of x is less than equal to 0. Because we want less than equal to sign here, so we multiply both side by negative sign, right? So what we get is, this is, so from here we can say that f must be concave and my gi's also must be concave. Okay. Any doubt in this? Okay. So again, so if anybody has any doubt, either he or she can unmute himself or herself at any time, or you can type it in the chat box. So if you are not comfortable with English, you can also ask in Hindi, whatever you are comfortable with. Okay. So now, if you look at a linear programming problem, then you have something like minimize f of x subject to gi of x is less than equal to 0. So you have all such constraints. Your f of x is linear, right? And your linear functions are always convex as well as concave, right? Because they are linear, right? So they satisfy this kind of property also, and this the concavity also. And same holds for your constraints also. So any kind of linear programming problem that you have is a convex optimization problem. Okay. Now, if we look at the next step, that is our quadratic program problems. So you can write a quadratic program problem in a generalized form as minimize C transpose x plus x transpose qx subject to gi's of x is greater than equal to less than equal to 0. Okay. Now your gi's are linear, right? So they are both concave and convex. You need not worry about them. So if you want to check the convexity of your objective function, then it turns out that if your q is positive semi-definite, then your quadratic program is convex. Why? Because if you take Hessian of your this, let's call this f, then the Hessian is given by q. And how do you check convexity of any function? If its Hessian is positive semi-definite, then it is convex, right? So for this case, you have your Hessian equal to f, and if your Hessian is equal to q, and if your q is positive semi-definite, that means your quadratic program would be a convex optimization problem. Okay. Any doubt till this point? Then we'll move to a few questions related to whatever we have talked till now.
Sir, all linear programming problems are convex.
Yes.
Yeah. Okay.
Okay. Because if you remember, let's say, what we talked when we talked about any convex function. Okay. So what did we say? That if, let's say, this is my function, if I join any 2 points on the curve, right, then this line should lie above my curve. Okay, that was our motivation and definition for a convex function last time when we talked. Now if you have, let's say, some linear line, that is, your function is a linear function, then if you join 2 points uh, on this, then obviously your f of x is lying less than equal to the line that you drew between these 2 points, right? And it is also greater than equal to the lines that you draw, because it is equal, that the lines are overlapping. That's why your linear functions are convex as well as concave. Okay. So if you now look at 2-3 possible scenarios for convex optimization problem, that is your minima, if you have something of form minimize f of x subject to gi's, so all these fx and gi's will be convex because they all are linear functions, right? So the complete setup becomes a convex optimization problem. And similarly, whenever you have concave here too, whenever you have convex, we need not worry about them because the straight line takes care of all these problems. Okay. Okay. So here is the first problem, sort of an easy one. So the question says, let's say you have a quadratic programming problem of form minimize z is equal to c transpose x plus x transpose qx. Okay. And you have some constraints, ax is less than equal to b and x is greater than equal to 0. So when does this become a convex programming problem? The question is this. Okay. So as I mentioned, its constraints are linear. Okay. So you just need to check about your this objective function, and your objective function is convex if your q is positive semi-definite. Okay. So if we had maximization over here instead of minimization, then your q must would have been negative semi-definite. Okay. So for this case, this option is correct, that your q is positive semi-definite. Okay. Okay. So this problem, I'll give you a hint and first let you try, and then I'll try to solve. Okay. So you are given with a function of two variables, and you have been asked to check whether this point minus 2 comma 2 is a point of local maxima or local minima, or is it a stationary point or is it not a stationary point, right? So how do we check for stationarity? So first step would be to check for stationarity. That is, you will calculate the gradient at the particular point. So you will calculate it at minus 2 comma 2, and if this is equal to 0, then it is a stationary point, right? Then next step would be to check the Hessian, whether it is positive semi-definite or it is negative semi-definite, and based on that you can choose whether it is a local minimum. So it's 6:38. I'll wait till 6:40. Please try this question and let me know what answer you guys are getting. Then I'll try to solve this. Just calculate the gradient and see whether it's equal to 0 or not. If you get it equal to 0, then calculate the Hessian and then look at its principal minor to infer whether it is positive semi-definite or negative semi-definite. I request you to please at least try solving. Then it will be more easier to it will be more easier for you to solve the assignment problem, which would be similar to these problems. What answer did you guys get? Okay, I'll try solving this now. Okay, so you are given with f of xy is equal to x square minus y square minus 2x minus 2y plus 4, right? This is minus x square, this is xy minus x, right? So what I said, step 1 is to find the gradient. That is, you have to check whether this is a stationary point or not. So how can you check whether a point is stationary or not? So you need to just find the gradient and check whether it is equal to 0 or not. Okay. So let's find the gradient. What is gradient of f? This is my del f by del x, and the second component is del f by del y. Okay. So let's find the partial derivative of f with respect to x. So I would get from this term, I'll get y minus 2x. There is no x in the third term, so I'll get 0 minus 2. In the last two terms, there is no x, so I'll again get 0. Okay. Now let's find this partial derivative with respect to y. So there is this xy where, so I'll get x. Then there is no y term in the second term, so 0 minus 2y minus 2. Okay. So now let's put values minus 2 comma 2 in place of x and y. So what do I get? I get 2 plus 4 minus 2, right? Here I get minus 2 minus 4 minus 2, right? So I get 6 minus 2, this is 4. Here I get minus 8. Okay. So is this equal to 0? No, this is not equal to 0 comma 0. So whatever point was given to me, in fact, is not a stationary point at all. Okay. So if this would have been a stationary point, then we would have gone to Hessian and checked whether my f is whether this point is a local minima or not. Okay. So now in this example only, let's try finding a stationary point. Okay. So let's say the question was that you are given with this function and you have to find all the stationary point for this function. Okay. Now we have calculated gradient. So what we want to do is we want to create the gradient equal to 0. So we want y minus 2x minus 2 and x minus 2y minus 2 equal to 0. So what this would mean, this means y is equal to 2 plus 2x. Let's put it in the second equation. So this would mean x minus 2, 2 plus 2x. Somebody wants to join. Okay. 2 plus 2x minus 2 is equal to 0. Okay. So this would mean that x minus 4 minus 4x minus 2 is equal to 0. This would mean x. So this would be minus 3x is equal to 6. X would be minus 2. Okay. Now we need to calculate the y coordinate. So we calculated y to be 2 plus 2x. This is equal to 2 minus 4. That is again 2. So the point minus 2 comma minus 2 is a stationary point. Any doubt in this? Then we will go to checking the Hessian. Any doubt if you are given with some function, how do you calculate the stationary point for that function? Okay. So now in order to calculate the Hessian, we are given with, not given with, but we have calculated that my f of x is y minus 2x minus 2 and my f of y is x minus 2y minus 2, right? So what I need to do, I need to find f of xx, which is minus 2, right? What is f of xy? This I get to be 1. F of yx is also 1, and f of y is again minus 2. So what kind of matrix do I get? So I get gradient of f is equal to minus 2, 1, 1 minus 2. Okay. So now we have to check for positive semi-definite or negative semi-definite. So what is first order minor? So first order principal minors. So if you hide the this second column and second row, you will get minus 2. Second, if you hide the first column and first row, you will get again minus 2. So both of them are strictly less than 0. Okay. And what is the second order principal minor? So it is the determinant of this matrix, which is 4 minus 1, which is 3, which is greater than 0. So now, as I mentioned few moments ago, that for negative semi-definite, you want alternate signs for your principal minor. So this is less than 0. This is sort of greater than 0. So this matrix is negative definite. So the point that you got, that is minus 2 comma 2, sorry, minus 2 comma minus 2 is a local maxima. So when you have Hessian as positive semi-definite, it is local minima. When you have negative definite, then it is local maxima. Okay. Any doubts related to this question, whatever we did in this question?
Sir?
Yeah.
Yeah. Sir, where above you were explaining about the negative semi-definite, you wrote that first order principal minus should be greater than equal to 0. So is it necessary that J should be greater than 0, or alternate pattern is necessary for negative semi-definite?
So the first one should be less than 0. Second one should be greater than 0, and so on. So if I wrote it, I think I made a mistake again. Let me see where I wrote. Oh yeah, I made a mistake here. So the first one should be less than 0. Second one should be greater than 0. Third one should be less than 0, and so on. So you should begin with, so that's why, to avoid this confusion, what you can do is, you just take the negative sign. I should have, yeah, I also got confused here. So you just take the negative sign. So let's say this was my matrix that I had to check. So what is minus A? Minus A is nothing but 2, 2, 1, 1. Sorry, minus 1, minus 1. Yeah. Okay. So now if you look at first order minors, this is 2 and 2. Second order minor, that is my determinant, is 4 plus 1 is, that is 5. So now there is no confusion, right? Because you just have to check that everything is greater than equal to 0. Okay. So yeah, first one should be less than 0. Second one should be greater than 0. This way you should reach an alternate point.
Sir, we always check a maxima, local maxima or minima on stationary point.
Yes.
Yes. But here is minus 2 or 2 is not a stationary point as we see above.
So minus 2 comma 2 was not a stationary point. Then what we did is
But
we found out which point is a stationary point, and we got that minus 2 comma minus 2 is a stationary point. That's why we
yes,
check.
sir,
Yeah.
but last sentence of our example,
Mm-hmm.
here is minus 2, 2 is the local maxima.
There is a minus here also. This is minus 2 comma minus 2 is a local maximum.
Okay, sir.
Yeah. Okay. Thank you. So now this is the next question. So we have to check in every part which of them is a convex programming problem and which of them is not a convex programming problem. Okay. So how do we do that? So the general way of checking, So the standard way is minimize f of x subject to gi of x is less than equal to 0. Then my f and gi's must be convex. Okay. So let's look at the first part, that is minimize w is equal to 2x square plus 4y square plus this subject to this. Let's check, this is my f, this is my g1, right? So what is the Hessian for, I have to check the convexity of my function f, right? Or the w over here. So what will I do? I will calculate the Hessian, right? So what is my f of x? F of x is 4x plus 7, right? F of y is 8y plus 6. So what would my Hessian look like? Hessian would look like 4, 0, 0, 8. Okay. So this is a diagonal matrix. You can see that all the diagonal elements are greater than 0. So this is positive semi-definite, right? So f is convex. Now let's look at g. So what is my gx? This is 2x. Gy is minus 2. So again, the gradient that you get is 2, 0, 0, 0, right? So this is also positive semi-definite. Why? Because you can either look at principal minor, that is 2 and 0, and then finally the determinant is also 0, or whenever you have diagonal matrix, then your diagonal elements are the eigenvalues for your matrix, right? So all the eigenvalues are greater than equal to 0, that means that your matrix is positive semi-definite. So the first example is a convex programming problem. Can you give 1 or 2 minutes to check the second part? So it is 6:53. Please attempt till 6:55 and let me know this part whether this is a convex optimization problem or not. Then I'll attempt this one. Just give it a try. Construct the Hessian matrix and see what you are getting, whether it is positive semi-definite or negative semi-definite, this part. Okay, Rohan is saying that it is convex. So others can also try to verify. I'll start solving this now. So if you look at the constraint part, this is linear, right? So you need not check for the linear thing. It is obviously convex, right? Now, if you look at just the z part, it is b. Now zx is minus 12x, right? And so this is a maximization problem. So what we need to show that your z should be concave, right? Or minus z should be convex. So if we now name write f as minus z, that becomes 6x square plus 4y square. So you get your f of x as 12x and f of y as 8y, and your Hessian matrix would look something like 12, 0, 0, 8. This is again positive semi-definite. So your minus of z is convex. That means your z is concave, and hence this problem is a convex optimization problem. Again, let's try for the third one. Okay. You guys can also attempt the third and fourth part and let me know which is not convex, right? So let me try the third one till then. Whoever has done, you can attempt the next one. So for the C part, this is minimization. So we'll just check for W. So Wx is my 2x plus 2y, right? And Wy is 2x plus 2y minus 4. So my gradient of W would look something like this is 2, this is 2, then this is also 2, this is also 2, right? So first order principal minus would be 2, 2, and the second order principal minus would be 0. So this first W is convex. Now let's look at the constraint, that is let's name it G. So G is x square plus y square minus 3. Okay. So what is the gradient of G? So this is 2, 0, 0, 2. Again, this is positive semi-definite, and hence this is also a convex O. So although the last part is only left, and that should be my concave one, sorry, that should not be a convex programming problem, but let's attempt the D part also. So this is D. This is maximization. So we'll take minus z, that is minus 3x square plus 5y square plus xy. Now the constraint is linear and hence convex. So no issue related to the constraints. Let's look at the Hessian for this. So let's name this as f. Then f of x is minus 6x plus y. F of y is 10y plus x. Now what is gradient of f? This would be minus 6, 1, 1, 10. Now if you look at the first order principal minors, what are first order principal minors? This is minus 6 and 10, and that's why this matrix is indefinite. It is neither positive semi-definite, neither negative semi-definite. It's indefinite, and hence my D part is not a convex programming problem. Any doubt in this question? Anybody has anything?
Indefinite matrix explain.
Okay, so a matrix which is neither positive semi. Okay, so indefinite means, so it is not positive semi-definite or negative semi-definite. So if you look at the first order principal minors, the signs were different. Okay, so for positive semi-definite, you wanted everything to be greater than equal to 0. For negative semi-definite, first order principal should be less than equal to 0, right? But one of them was less than 0 and one of them was greater than 0. That's why this is an indefinite matrix. Was that clear?
Oh, okay, sir.
Yeah. Okay. Okay, so I think this should be an easy question. So the question is, consider an optimization problem P, which is maximize Gx subject to f of x less than equal to 0. Then P is a convex programming problem if. So you have max g of x subject to f of x less than 0. So please tell me which of them is correct. We have done 4 questions related to this. So I'm expecting an answer from you guys. So you want this problem to be a convex optimization problem. So what should be the condition on G and F? So this is option A, B, C, D. Please let me know which one is correct. Just type it in the chat box, which is the correct option.
Option C.
Okay, option C says F is concave and G is convex. What others have to say? Why option C? So you have a maximization over here, and
Yes,
what
sir.
you are maximizing? G of x. So when you are maximizing g of x, whatever is written over here, this should be, so this is same as minimize minus g of x subject to f of x is less than equal to 0, right? So this term should be convex, right? So whatever is written here should be convex. So if minus gx
So
is convex,
D.
what does this
D
mean?
option is
Gx is concave and f of x is less than 0, so f should be convex.
yes,
So
sir.
whatever term is here, this should be convex. So G is concave and F is convex. So D option is correct. Was I clear, Rohan and Nishtha? Why option D is correct? Okay, thanks. Whoever has unmuted, can you please mute yourself? Thank you. Okay. Okay. Now, till this point, okay. So this is a long 2-hour session. So let's break for 2 minutes, 2-3 minutes. I'll start at 7-6. So till now we talked about constraint optimization. Sorry, unconstrained optimization. Now we'll talk something about constraint optimization. Okay, and also some numerical techniques for optimization. So because this is a long 2-hour session, so let's take a break for 2-3 minutes. We'll resume at 7-6. Okay, so let's begin. So till now we talked about unconstrained optimization, where we had something just like minimize or maximize f of x. Now let's say somebody adds some extra condition that you should also satisfy these conditions. Okay, then how to go about it? So now this is a necessary condition, not a sufficient condition. Similar to the gradient condition that said that this is 0, this is a necessary condition. So for constraint optimization, similar to this condition, we have this necessary condition. So first thing is that let's say your x bar belongs to the feasible region. That is, your x bar must satisfy gix is less than equal to 0 for all I. Okay. Now if this is true, and let's say your x bar is a local optimal point, then it must satisfy the following conditions, which are known as KKT conditions. Okay. So for unconstrained optimization, the only condition that it had to satisfy was that the gradient should be the gradient should be equal to 0. Now for the constraint optimization, you have to satisfy 4 problems. Okay, 4 conditions. First is, now rather than just taking the gradient of f of x, we have an extra term here which takes the gradient of all the constraints along with the Lagrange multiplier. You call it Lagrange multiplier, lambda is, and its sum is equal to 0. Okay, so earlier you had just the gradient equal to 0. Now you have these terms equal to 0. The second condition is nothing but the repetition that your x bar satisfies all the constraints. So this is not very important. The third term says that your lambda is, okay, so this is lambda I bar and lambda is same, multiplied with all the constraints at that point should be equal to 0. And your fourth constraint is that all your lambda is should be greater than equal to 0. Okay. So this is something that is known as KKT conditions. We'll solve problems on this. Okay. So this was the necessary condition. Now, if your f and g have 2 extra properties, that is your f and g are sort of convex functions, and they are differentiable, then this condition becomes your sufficient condition for x bar being a local optimal point. Okay. So just remember these 4 points and we'll solve the problem based on this. Okay. So I'll solve one and I'll ask you guys to solve another. So the question is, consider this programming problem. Okay. So z is equal to 2x square minus 2xy plus y square minus 5x minus 2y, subject to some constraint. Okay, so let's write it cleanly. So minimize f of xy is equal to something subject to, there is some g1x which is less than equal to 0, and then we have x comma y greater than equal to 0. Okay, and it says that alpha comma 9/2 is an optimal solution. Then we have to find the value of alpha. Now if alpha comma 9/2 is an optimal solution, then it must satisfy all my 4 KKT conditions. Okay, so let's build these KKT conditions. Now how many constraints I have? So I have, you can see that there are sort of only one constraint, but these constraints will also count. So xy greater than equal to 0 is equivalent to minus x comma minus y is less than equal to 0. So let's try to build the KKT condition. So from first condition, I have gradient of f plus summation of gradient of gi into lambda I will be 0. Okay, so now this would be a vector, right? So gradient of f would be a vector, gradient of gi's would be a vector. So we'll get two equations from here because this is a function in x and y. So what is f of x? F of x is 4x. So right now I'm calculating gradient of f. Okay, so 4x minus 2y minus 5, right? Minus 5 plus, now I'm coming to the constraint part. So this is lambda 1 into 3. Okay, and this constraint has become 3x plus 2y minus 20 is less than equal to 0, right? And you have one more with respect to mu1 equal to. So I'm using mu1 and mu2 for these two conditions because these conditions are sort of different from our usual constraints. So I'm using a new variable so that we remember what variables we have. Okay. Now, if you take its derivative with respect to y, we'll get another condition, that is minus 2x plus 2y minus 2 plus 2 lambda 1 from this part is from constraint minus mu2 is equal to 0. Okay. Now, as I said, that second condition is just the feasibility check. So let's sort of ignore this condition for the time being, and we'll go to the third condition. Okay. Third condition says that lambda 1 into, so this is 3x plus 2y minus 20. Okay. This is 0. And this is mu1 into, this is your minus x is equal to 0, and mu2 into minus y is equal to 0. Okay. Now we will have some inference. So we have these uh, conditions or the equations that we have. Okay, and we want to find the value
So
of, yeah,
why we take mu1 of minus x equals to 0? म्हणजे why we take minus x here?
because the constraint that was given was in form x comma y is greater than equal to 0, right? But what we know is the standard form is when my gi of x is less than equal to 0. So we will convert all the constraint in the form less than equal to 0.
Okay.
That's why we have a minus x over here
Okay.
and minus y. Okay. Now the optimal point that is given to us is alpha comma 9 by 2, right? So we know that my y is not 0. In fact, my y is 9 by 2. So that would mean that my mu2 must be equal to 0, right? So my mu2 is 0 because y is not equal to 0. Now we are putting these values over here, right? So that would, let's call this equation 1, 2. Okay. So now if you put this value in equation 2, what we get is, so we get something like minus 2 alpha plus this is now 9 by 2 into 2y, this is 9, right? I think this should be plus only, yes, this is with respect to y, this should be plus. Yes, this is plus. Yeah, this is correct. Okay, and then this is minus 2 plus 2 lambda 1 is equal to 0. Okay. So this would mean that Yes, let's leave this thing over here. And now if you put these values in equation 1, then what do we get? We get 4 alpha minus 9 minus 5 plus 3 lambda 1 minus mu 1 is equal to 0, right? So now we need to find the value of alpha using the equations that is sort of given to us. Okay, and we'll try to do this. So yeah. Also, if you just a second. So yeah, if you look at one thing carefully, so if you look at this portion, this is what is the gradient of f, right? This is my gradient of f. Okay. So I just need a condition. Yeah. So let's say if my point is alpha comma 9 by 2. Now if my alpha is 0, what would happen? Let's look at the situation when my alpha is sort of 0. Okay. So if my alpha is 0, then this term would become let's look at the second equation. So second equation would become, so if my, let's say my alpha is 0, in that case this equation would become, this is 7 plus 2 lambda 1 is equal to 0, or this would mean my lambda is minus 7 by 2. So this is non-zero, right? Lambda 1 is non-zero. And what is the interior part of this? So this is 0 plus 9 by 2 into 2 is 9 minus 20 is 0. So what this would mean is that the multiplication of two non-zero values is getting to be 0. So I got lambda 1 from this equation to be non-zero, and this term inside this is also non-zero. And when I'm multiplying two terms, then I'm getting 0, so which is not possible. So this means that my alpha is also non-zero. Okay. I hope I made the point why my alpha is non-zero. Okay. So now, as my alpha is also non-zero, so I can say that my x is also non-zero, and hence my mu1 is also 0. Okay. So we can just eliminate this mu1 also from here and take this to be 0. So now we have two variables and two equations to solve. So this is minus 2 alpha plus 7, or we can just write it in a better way. So this is 2 alpha, sorry, this is 2 alpha minus 2 lambda 1 is equal to 7. So I just sent this 7 this side and multiplied by minus 2 out. So this is 4 alpha minus 14, or we can just take plus 3 lambda 1. This is lambda 1 is equal to 14. Okay. And we just need to find alpha, right? So this would mean that my, so if you look carefully, you can just multiply this by 2, right? And then you will get 4 alpha minus 4 lambda 1 is equal to 14. You just subtract these two, you will get minus 7 lambda 1 is equal to 0, or lambda 1 is equal to 0, right? So if you put lambda 1 equal to 0, what you get? 2 alpha is equal to 7, or alpha is equal to 7 by 2, right? So you have obtained the value for alpha, which is your 7 by 2. And this is what was asked from us, right? Any doubt in this question? So I got
Sir, please
So I
state the
got
non-zero part where you prove that x is non-zero.
where I said that x is non-zero.
Yes, sir. That you prove mu1 is zero, not x.
Yeah. So let's say my x was 0. Okay. So my solution is given to be alpha comma 9 by 2. Sorry, the solution is given to be alpha comma 9 by 2. This is my x component. So there is two possibility for this, that it is either 0 or non-zero. Okay. Now let's say if my x was 0. Let's say if my x was 0, what would that mean? So if I put everything in this equation 2, right? So I'm putting everything in equation 2. That is my x is 0, but y is non-zero. So let me just give me a second. Let me just copy this thing below. Sorry. Yeah. So these are the conditions that I obtained. Okay. Now we have already inferred that my mu2 is 0, and we just want to check about x, right? So I put x is equal to 0 here. So the first term becomes 0. Second term is 2y. 2y is y is 9 by 2, right? So this is 9 minus 2 plus 2 lambda 1 is equal to 0. What this means? That my lambda 1 is minus 7 by 2. Till this point, is it clear that I got my lambda 1 is equal to minus 7 by 2 from equation 2 if I assume that my x is 0. This much is clear?
Yes, sir.
Okay. Now we have this condition also, right? From the third condition of the KKT, we obtained these three conditions. Okay. So if we look at this condition now, my lambda 1 term is non-zero, right? So the only possibility to make this thing 0 is that my 3x plus 2y minus 20 should be equal to 0. But I know that my x is 0 and my y is 9 by 2. So 0 plus 9 by 2 minus 20 is 0. So this is not possible, right? So this is sort of contradictory. That's why my x can't be 0. Okay, so x is non-zero. Now if my x is non-zero, if I put it in this condition, then this makes my mu1 is equal to 0. Is it clear now? This is how
Yes,
we
sir.
eliminated the case that x equal to 0 is not possible. Okay. Okay. Now we have another question. I solved one based on KKT condition. So you guys can try solving this one. I'll give you ample time. So this says that I'll also copy the KKT conditions here, a slightly cleaner one. Just give me a second. So this is the question. I want you guys to attempt it. Okay. So I've also included the KKT conditions here that you can use in this question. So this question had a missing point. I have included that point. So using the KKT condition, you have to find the value of beta such that this point 1 comma 3 is an optimal point for this given constraint optimization problem. Okay, so here you have to find the value of beta so that this point 1 comma 3 is an optimal solution. Okay, I have included all the condition. You just need to write the KKT condition for this and then eliminate some in similar way to what we did in the last question and tell me the value of beta. So this is 726 right now. I'll give you a good 4 or 5 minutes to solve this question. So please try solving this question, and I'll start solving this at 7:30, let's say. Okay. So please attempt this question. At least try writing the KKT conditions and both. These are the conditions that you need to write. So this is your F, and this much is your G1. This X condition would give you G2, and then your Y condition would give you G3. Just attempt this question so that if you will solve, then you will gain more confidence in solving similar questions. I can solve this straight away, but then it won't be very beneficial for you. Okay, sorry, I didn't saw the message, Rohan. Is it better now? I'm really sorry, I didn't saw that message. Okay. I'll give you 2 more minutes for solving. You can try. If so people are attempting, then I can wait even longer. So please let me know. So, Kushal, I don't know the answer actually. Let's see what others
Trying.
count. What is the answer?
So trying
What?
solving.
I was not able to hear you clearly. Okay, we can start solving now. If somebody is attempting, I can wait a bit. So if somebody is attempting, please let me know, or I can start. Kushal, let's see whether we get 0 or some other answer. Okay, let's start. So let's try constructing our KKT condition. Based on first condition, we'll get two equations. First with respect to derivative, first from with derivative with respect to x, and another from derivative with respect to y. Very similar to the previous question. We will have 4x. So I'm taking derivative with respect to, okay, yeah, yeah. So we have 4x, right, plus beta times y minus 4. Okay, so this is from the first part. Now with respect to your constraint, so we have lambda 1. So we have only one constraint, so let's write it lambda only, not lambda 1 again and again. And this is 1, okay, because there is only x term here, and minus mu1, similar to the last one. This is equal to 0. Now again we have with respect to y, this is beta x plus 4y minus 6 plus 2 lambda minus mu2 is 0. Now based on third condition, this KKT condition, third condition, we have uh, lambda into x plus 2y, right, x plus 2y minus 2 is equal to 0, and mu1 into minus x is equal to 0, mu2 is equal to minus y is equal to 0. Okay, so yeah, now the point that is given to us is x comma y is equal to 1 comma 3, right? So again, a very similar observation, that would mean that my mu1 is equal to 0 because x is not equal to 0, mu2 is equal to 0, right? And let's see what else we have. So, yeah. Okay. So let's put the value of x and y in my equation 1 and 2, and let's see what do I obtain. So I obtain 4 into 1 is 1, this is 4, right? And then I have just give me a minute. Okay. Then I have 3 beta, and this is minus 4, right, plus lambda, so 0. And from equation 2, I have beta plus 12 and 6 plus 2 lambda equal to 0. So let's try to solve this for beta. So this would mean that 3 beta plus lambda equal to 0, and this would mean beta plus 6 plus 2 lambda equal to 6. Okay, so I think this is what we should obtain, and yeah, beta plus just a second. Yes. Okay. So now this question sort of became sort of easy. If we look at this point, now my x plus 2y is 1 plus this is 6 minus 2. So this term is 7 minus 2, that is 5. And this has become, so this is non-zero and lambda becomes 0. Okay. I think I have miswrote this point. But yeah, if this becomes 0, then your beta becomes 0, right? But then this would contradict this point. So this in fact is not an optimal point. Kushal, your answer was right, but I'll just change the point. I think I have made a mistake with the point in writing the question. So just give me a second. So this is x of so I want to make this thing, so this is half. Okay, so if we change the question a bit and make this point as half and 3 by 4, I think I made a mistake in writing the question. So let's try solving it then. Okay, so the steps are same, but now we have a non-zero lambda, right? Otherwise the question was not making a lot of sense. So again, my mu1 and mu2 would be 0 as before. And now if you look at the interior, right? So this is half plus 2 into 3 by 4 minus 2. So this is 2 plus 3 by, this is half plus 3 by 2 minus 2, which is 0. So the interior part is 0. So my lambda need not be 0. Okay. Now we will try to solve this question. Okay. So let's, based on whatever we had, Kushal, I think your answer was correct. But the second part was contradicting this value because this in fact was not an optimal point. Okay. So now we will put this value of x and y. So this x is half and 3 by 4 in my equation 1 and 2. So we obtain 4 into half, right, plus 3 beta by 4 minus 4 plus lambda equal to 0. So this can be rewritten by as, so if we sort of take 4 LCM everywhere, so this is 8 plus 3 beta minus 16 plus 4 lambda is equal to 0, or this would mean that 3 beta plus 4 lambda is equal to 8, right? And if we put it in the second equation, this is beta by 2 plus 3, so 3 by 4 minus 6 plus 2 lambda is equal to 0. This would mean beta plus 6 minus 12 plus 4 lambda is equal to 0. This would mean that beta plus 4 lambda is equal to 6. Right. Now, if we just find the beta, this would mean that my 2 beta is nothing but 2. If we subtract this, let's call this 3, let's call this 4, so 3 minus 4 gives this thing, or beta is equal to 1. Now this makes sense. Okay, so the point that I chose was not a optimal point, that's why we made a mistake. So yeah, this is how we solve questions based on KKT condition. Any doubt in this?
So if we have given, we take a condition u1 of minus x equals to 0 and u2 of minus y equals to 0, and we have a condition that is y2 equals to 0.
This is
Sorry, y.
multiplication. This is not a function, but multiplication of u1 with minus x. This is
Or
multiplication.
if we have given a y equals to 0, then can we take a u2 equals to 0, or
Then we don't know anything about u2. If we have y equal to 0, then you will also have to solve for u1 and u2 in this equation. Then your y term will get eliminated, right? So this term will become 0. But then you will have to find solution for u1 also. Okay. Okay. Okay, so till now, whatever we did, so when you have to find a solution, so this KKT condition was necessary condition, and it became sufficient when your f and gi's were convex plus differentiable. Okay, differentiability is fine till some extent, but this condition that all f and gi's should be convex is a very strict condition. So in real life, you will get many situations where this thing is not true. Okay, so there we still, the research is on, but we don't have very great methods to solve the exact solution. So we look something that is known as numerical solution for our optimization. Okay, so these are not exact solutions, but solutions which are close to exact solution. Okay, so one of the common method is steepest descent. So what you do in this kind of problem, let's say you want to minimize or maximize some f of x. Okay, this is again for unconstrained. Okay, so what you do is you start with some point x0. Okay, and from x0 you move, let's say you start from x0, and then you look for a direction in which f of x is decreasing. So starting from x0, you look in some direction in which your f of x is decreasing, and you move a bit in that direction. Okay, so what you do is from x0 you obtain a x1 by sort of moving in that direction. So you can write it as minus some alpha times d1. Okay. Again, from x1 you obtain x2 by moving in that direction by d2. You can replace this by plus also if this d is a descent direction. Okay. So now when we talked about gradient, we said that the gradient of any function is the direction in which function ascends maximum. So we know that this is the direction in which our function will ascend maximum. So if we take negative of our gradient, that is the direction in which our function descends maximum. So an algorithm that is also known as gradient descent or steepest descent can be formulated. So you begin with some point x0. Okay, and from that point x naught you construct x1 by taking x naught minus some alpha times of gradient of f. So if you look at this term, this is the direction of descent, and this is the amount that you move in that particular direction. Okay, so let's try to understand this with the help of an example. So similarly, you can obtain x2 is equal to x1 minus some. Again, this alpha can be varying, right? So you did not fix a single alpha, but this alpha can vary from iteration to iteration based on your need. Okay, so alpha saying these sessions are recorded. If you go to the course web page, in the end you will find an option of problem solving session. If you click on that, you will find all the links to these sessions. Okay, and also these whatever I'm scribbling, that thing is also included over there. Okay. So yeah, so this is what is known as steepest descent method. Okay. So here is a question. We'll try to understand this with the help of a question, and then we'll see why this method is very useful for machine learning algorithms, and some peculiarities regarding that. So we are given with the function f of x, okay, and we have been asked. So using the steepest descent algorithm, the value of f at the next iteration for an unconstrained optimization. So first of all, we need to find x1 and then find the value of this function at x1. Okay, this is what is given to us, and we have to begin with 1 comma 1 transpose. Okay, so first step would be to calculate gradient. Okay. So what is gradient of f? So this would be 4x minus 3y plus 1. Okay. Right. Now gradient of so this derivative of x is equal to y would be minus 3x plus 6y minus 3. Now we have to find the value of gradient at 1 comma 1. Okay, so this is given by 4 minus 3 is 1 plus 1, 2, right? Minus 3 plus 6, this is minus, this is 3 minus 3, I think this is 0. Second term is 0 if I'm not wrong. Yeah, okay. So this is the direction that we got. Now what we need to do is, we need to, so my x1 is 1 comma 1 minus some alpha times 2 comma 0. What it is? So this would be 1 minus 2 alpha comma 1, right? Now how do we calculate this alpha? So whatever method I'm telling you right now is very helpful when you're solving it mathematically, but this is sort of not very useful when you're sort of optimizing a machine learning algorithm, because you will have to do an extra step of optimization that would take a time, and training this machine learning algorithm already takes a lot of time. So if you want to also optimize this alpha on top of it, so that is not a very good idea. Okay, but mathematically I'll show you how to solve this. Okay, now if you want to move, let's say, from x naught in this direction to reach a point x1, what would you expect? You would expect a point x1 for which your function f of x has a minimum value in this direction. So you want to move till a point so that if you are moving in that direction, your f has attained the minimum value with respect to that direction. So if you move a little further, your function values increases, or if you just stay a little back, your function value is still greater than what you would have obtained at x1. Okay, so now if you write f of x in terms of this thing, this would be 1 minus 2 alpha whole square minus 3 1 minus 2 alpha, because y is 1, plus 3 plus 1 minus 2 alpha, right, minus 3. Okay, so these terms get cancelled and you are left with 1 minus 2 alpha whole square minus 2 times 1 minus 2 alpha. So you want to minimize your f of x with respect to alpha, right? So what you will do, you will take d of f with respect to d of alpha. This is 2 1 minus 2 alpha, and if you further differentiate, this will be minus, right? Minus, so this becomes this would have become 1 minus 2 alpha square minus 2 plus 4 alpha. So this is plus 4, right? So this is minus 4 plus yeah, I think this is correct. So yeah, so this would be plus again, yeah, plus 8 alpha. This 4 and 4 are cancelled out. This shouldn't happen. Let me see if I've made some calculation mistake. So this is 1 minus 2 alpha comma 1. So this is 2x square. Yeah, this is 2x square. So I missed a 2 here, right? This is 2x square. So there would be one more 2 over here. So this would be 4 here, right? So then this thing would become, yeah, this thing would become minus 8 plus 8 alpha plus 4. This would imply that 8 alpha, and we want to equate this to 0, right? And then this 8 alpha is 4 and my alpha is half, right? So yeah, so starting with initial guess, then we want to find the value at that point, right? Again, this is 4 to the 8 minus 16. I'm making a lot of calculation mistakes. So this is 16, lambda is equal to 4 and lambda is 1 by 4. Okay. So we have got the value of, I don't know why I wrote lambda, but this is alpha. So we have got alpha is equal to 1 by 4. Okay. So we got our x1 point to be 1 minus 2 alpha. This is 1 minus 1 by 2. This is 1 by 2. And second term is 1. So we have to find the value of x1, right? That you can easily do by just putting it here, over here. So we have some very less time. So I'll talk more about the machine learning thing here. Okay. So you saw that finding this alpha involves an extra step of differentiating and then calculating the value and then reaching to that point. So generally, when we are optimizing some machine learning loss function, we don't explicitly find alpha. Okay, what we do is we generally begin with some value of alpha, let's say 0.1, and with steps we keep on decreasing this value. Well, let's say for first 4 steps of your optimization, first 4 iteration, you stick with value 0.1, and from 5th step onward you reduce it to, let's say, 0.05. Okay, and so on. You can sort of keep reducing it, and generally this process works well in practice. Okay, even though we are not going for the exact alpha, sort of choosing alpha arbitrarily works well in practice, and also because you are sort of choosing alpha arbitrarily, this in some sense also helps you regularize better, okay, or generalize better, because you are not reaching the exact minimum point for your training error, but you're reaching an approximate minimum point that will help you generalize your future test points better. So in practice, just a summary that in practice, you might not need to find the exact value of alpha, but you take some alpha and you sort of keep reducing it with iteration. Okay, yeah. So now this is one point. Another point is sometimes when you manually reduce this value of alpha, you might not converge to some minimum, right? So there is a condition that either you are moving too slow or you are shooting the minimum point. For example, from here you moved here, then you moved here, then here, and you sort of shooted the barrier. So what is the solution to it? So there are sort of many inbuilt optimizers. One example is Adam optimizer. So, and there are many new like inbuilt optimizers also that helps you choose alpha automatically. Okay. So when you are defining your loss function, you can when you are optimizing, you can mention what optimizer you want to use. I sort of generally use Adam optimizer, and then the process of choosing alpha is taken care of automatically. When I'm talking about Python, when you use Python to train your model. Okay. One thing is this that I wanted to mention. Okay. Let's sort of quickly look at this Newton method because this is related to this content. I wanted to talk about stochastic gradient descent also, but let's see, maybe some other day I'll talk. Okay. So yeah, what is Newton method? So Newton method was originally not developed for solving optimization problem, but this is a numerical technique for finding root of an equation. Let's say you have some f of x and you want to find a point such that your f of x is equal to 0. Okay, but you don't have any explicit solution to find it. Then you use a numerical technique called Newton's method to find the root of the solution. Okay, so you begin with some point yk and then you move to the next point yk plus 1 given by yk minus, let's say your function is f, so it would be f of yk divided by f dash of yk. Now people have proposed to use this to optimize a sort of function that is given to you. Let's say you want to optimize f of x, then what you do, your first step is to find f dash x is equal to 0, right? So if your f of x is equal to 0, you are finding root using Newton's method. Now you want to find the root for your f dash x. So let's say you begin with some point xk, then your xk plus 1 is given by, this is this is minus f dash xk. Now your f of x is replaced by f dash divided by f double dash of xk, when your f was a single variable function. Okay. Now because your x that we are dealing, this f that we are dealing with is a multivariate function, then your f dash x is replaced by gradient and divided by f double dash x means that you are multiplying it with the inverse of your Hessian. Okay, so the Newton method is given by xk plus 1 is equal to xk minus Hessian of f at that point inverse gradient of f xt. Okay, so this is how we reach to Newton's method. Let's solve an example based on it. Okay. Okay, so we are given an unconstrained optimization problem. Okay, and we have been asked to find the first point obtained via iteration using Newton method, and we are also given the x0, and then we have to calculate x1 minus x1. Okay, so let's quickly find out this. So what are the terms required in Newton's method? First is gradient, second is Hessian. So let's find gradient, and if this time I make a calculation mistake, please let me know there, so that we don't have to change everything at the end. So f of x is 16x minus 4y, right? So I think this is very small for you guys, so I'll zoom down. And the second term is minus 4x plus 10y. Okay. Better way is to write f of xy. Let me write it on. This is 8x square minus 4xy plus 5y square. Okay. Now what is Hessian? Hessian would be 16 minus 4 and 10. Right? This is what you will obtain as your Hessian. And now the gradient at the point that is given to you, that is 5, 2. This is, so 80 minus 16, so 80 minus 8, and this is minus 20 plus 20. This is 72 and 0. Okay. Now this is your Hessian. This is h of f, because there is no x involved, so this is okay. What is its inverse? So this would be 1 divided by 160 minus 16. Okay, and this terms get swapped, 10, 16, 4, 4. Right. So this is 1 by 144 times 10, 4, 4, 16. So what is the point x1? So you had to find x1 minus x0, right? So this is x1 is equal to x0 minus Hessian inverse gradient of f. So x1 minus x0 is just minus of Hessian inverse gradient of f, right? This is what you have to find. So this would be a bit of calculation, so let's try to do it. So this is 1 by 144, 10, 4, 4, 16, and this is 72, 0. This is 1 by 144, and this is 720. Okay, this is 0, and this is 72 into 4. So if you look at this sum, I think this is, yeah, 4, this is 5, right? If you divide 720 by 144, you will get, yeah, this is 5. And the second term that you obtain is your, this is 2. If I am not wrong, this should be the answer. Okay. And you have a minus sign in front of you. So this would be minus, this will be minus 5 and minus 2. So you should get minus 5, comma minus 2. This is your correct answer. Yeah. There is a minus sign also. Any doubt in whatever we have discussed till now? Then I'll just briefly tell you what is penalty function method. I don't have any example based on it, but and there is no question in the assignment also based on it, but I'll still want to just.
Using step-based descent method, the direction d2 to determine second iterative point x2. How can we calculate x2?
So from now, if you have reached x1, right? So you
Yeah.
want to find d2, right? Then this is just the
Yes, sir.
gradient of f at x1. This is your descent direction. Negative of this is your descent direction.
Okay. The negative of gradient of f of x1.
This is the descent direction. Okay. Okay. Okay, now let's go to what is known as penalty function method. So these numerical techniques that we just discussed, the two of them, that is steepest descent and the Newton method. These are for your unconstrained optimization. Now, what about constraint optimization? Let's say you have minimize f of x subject to some gi of x is less than equal to 0. Okay. Now, what we do is, let's say there is a set S which is formed by taking x such that g of I x is less than equal to 0 for all I. So these are the x which satisfies all your constraint, or this is your feasible reason. Okay. Now, if you define a function that is known as your penalty function such that this function is 0 whenever your x belongs to S and is infinity whenever your x does not belongs to S. Okay. And now, if you minimize this thing, that is your f of x plus p of x, rather than just minimizing of x, what would happen is, so if you encounter a point which is a part of x, then this would be same as minimizing your f of x, right? Because your p of x would become 0 whenever your x belongs to S. Okay, so this would be same as x belongs to S as your original problem. Now, if your x does not belongs to S, that would mean that the function value would be infinity, and you won't want that, right? You want a minimum value over here. So you won't land a point where your x does not belongs to S. Okay, so that means that minimizing this function is same as minimizing f of x subject to your gi of x is less than equal to 0. So what people use is, now rather than looking at this constraint optimization, we convert it to unconstrained optimization of this form. This might look ugly because of this infinity over here, but because we are using some numerical techniques, this is good. Okay, because we are going to use numerical techniques on top of it. But there is one problem associated with it, that is, if you look at this function, this is not even continuous, right? So we will have high jumps in this, and this would not be differentiable. Okay. So we propose an alternate penalty function, which is sort of good for us, which is summation of I is equal to 1 to m. So this is your all the constraints that you have. Maximum of g of x, okay, comma 0, and square of this function. Okay. So this is an alternate p of x that is proposed. If you look carefully, this would also be similar to your original optimization problem. So now again you can solve your f of x plus alpha times f. So you can minimize eventually. Minimize. There can be other alternate penalty functions too, but these two are quite common. So yeah, this is what I had prepared for today. If anybody has any doubt, you are free to ask. One thing that I missed is related to stochastic gradient descent and your those kind of things, but I have covered them in earlier lecture. So probably whenever I'll get some time left from in the next session, I'll sort of try to revisit that thing based on whatever we discussed today. Anybody has any doubt in whatever we have covered till now?